next time, I've got them right here. I didn't have a chance to score much. Basically, I didn't get it, but I'll take care of it. Now, our test tape, everybody's familiar. What is?
Oh, next Wednesday.
Just making sure. So, let me continue. Here's what I plan on doing. I know we had a long break. I'm going to go through radar again, and then I didn't get a chance to do Doppler, and we may start EMC, but I want to make sure we cover a few problems. I don't think I put anything up with radar, did I? Any problems? So we'll go over a few today. So this is radar again. So for radar, you basically have a transmitting antenna. And you've got some target out here. And it has a certain size, and the size is called a radar cross-section. And we call this RCS, and the symbol for it is sigma. And you've got to make sure, sigma we use for conductivity as well. This is the radar cross section, sigma, and it is in meters squared, and it's the size of the target. You could say this is really size. It's a distance r away. And I'm going to add a few things. So this is just the standard radar problem where you have a transmitting antenna. The transmitting antenna has a gain T, that would be the gain of the transmitter, and there may be a different gain of the receiver, but there's going to be, usually the gain of the transmitter and the gain of the receiver are the same for radar. And this is for a radar antenna, and this is the monostatic antenna, where the same location of the transmitter and receiver. The transmitter and receiver have the same location. So the way I like to do this, because I asked this in the quiz, I asked for the power density just before it hit the target, and then the amount of power received back. But normally I start right here, and I want to find out what the average power density is on the target. I'll just call PAV sub T. So PAV sub T is going to be the transmitted power. I might as well say this. There's going to be the total amount of P transmitted right there. Do you remember how this goes? I try to make sure that everybody thinks this way. It's transmitted power divided by 4 pi r squared. Right? So that's the isotropic, if there was not an antenna in a sense, if it was just spreading out in space without any kind of focusing, that would be the power density on the target. Y'all with me? Then the gain of the transmitter sharpens it. So that's the amount of power density. It's actually going to be right here. And I almost always ask for this. Then the amount of power that's scattered by that target, or P, I'll call it scattered, is just P average on the target times the radar cross-section of the target. So now all that power is re-radiating. And as it re-radiates, it falls off as 1 over 4 pi r squared. Follow me on this? So finally, the amount of power density, or P average, that's back at the radar, and that would be right here, the actual P average that would be at the radar. This is going to be the scattered power density divided by 4 pi r squared. And there is no focusing. The radar cross-section has that built into it. So if there is any anisotropic kind of scattering, the radar cross-section would take care of it. It'd be a function of angle too, just like the gain would. Can you all understand that, class? Finally, the amount of power that's received back at the antenna will be this average power density, power density at the radar, and then it would be times the area. Do you remember what the area of the aperture is? There's a formula for it.
Lambda over 4 pi r squared.
The electrical size of an antenna is lambda squared over 4 pi times the gain. We'll call it gain of receiver. So it's going to be that times lambda squared over 4 pi times gain of the receiver. Now I'm going to put it all together in one equation. So if we started here and just took this and stuck it there, and then took that, stuck it there, and went all the way down, we'd get this. We'd say that P received is actually going to be P transmitter over 4 pi R. Well, I'll do it. I'll get the whole thing condensed. So it would be this. P transmitted, then you'll have 4 pi cubed here. You'll notice there's a 4 pi there, there's a 4 pi there, and there's a 4 pi there. So it's 4 pi cubed. Then it's over R to the 4 times gain of the transmitter, gain of the receiver, lambda squared times sigma. And that's the classic equation for radar. It really is. Then, the next thing I'm going to do, so that's the amount of power received if you have a given antenna and it's in a monostatic configuration with the same point where it's transmitting, the same point it's receiving, and you have a target out there. Now, the next thing I do, I want to go ahead and do is bistatic. This is almost the same, only now we're going to have a transmitter and receiver at different points. So this is going to be bistatic. You'll see the parallels. For bistatic radar, you're going to have a transmitting antenna. And it's going to have a gain of the transmitter. And there's a target out here. And the target has some sigma, which is the RCS. And this is going to be a range R1. So between the transmitting antenna and the target, we're assuming a range R1. Do y'all follow me? Then we're going to have a receiving antenna over here. And this will have the gain of the receiver here. And what we want, and this is going to be at a range R2. And now what we are actually interested in is the received power here at the second antenna. So this is bistatic. Now, does everybody follow me on this one? I just relocated the receiving portion at a different range. This is a much more difficult setup to get to work for a lot of reasons. Basically, because you have to have complete synchronization. It's called with something called a local, a very stable local oscillator, and I'll explain that in more detail later, or try to at least. So now for this one, when we take a look at P receive, I always start here, start the transmit antenna. If there is no focusing ability, find the amount of power density of the target. So it's always going to be a transmitted power over 4 pi R squared, and this would be R1 squared. Y'all follow me? Just R1. This isn't a major step away from that, but y'all follow me? Take isotropic. And now I'm going to multiply it by the gain of the transmitter. So now that's the power density right there. Then I multiply it by the radar cross-section. And by the way, the radar cross-section will be a function of angle in general. And it's also a function of the aspect of the target. Let me explain this to you as best I can. So if you look at this phone, when it's flat like that, the actual observable cross-section, the optical cross-section, is very small, right? Goes like this, much larger, right? That's called the aspect of the target being a function, the radar cross-section being a function of that. But by the same token, also, this will look different depending if the radar is here or here, which is really the same thing as the aspect of the target changing. So in other words, this will be a function of angle in general, all right? And it's based on measurements, pretty much, sometimes simulations, but it's well documented. Now that's the amount of power scattered. Now I have to take that and it falls off isotropically. I've got to divide this by 1/4 pi, and now that's going to be, I had R1 here, this should be, which was R2, it should be R2. R2 squared. Now that's the power density back here. So if I gave you a problem, I could ask you for the power density here, the amount of power scattered, and the power density here, and you should be able to get all these things logically, the way I'm showing. Now the amount of power received is going to be that times the actual area of that receiving antenna. So it's going to be lambda squared over 4 pi again, and then it's times gain of the receiver. So if you look at that equation and this equation, you can see the only real difference is what? Now, instead of r to the 4th, you have r1 squared and r2 squared. Y'all follow me on that? That's there. So when we talk about for a bistatic antenna, P receive is equal to P transmit over 4 pi cubed, and then it's going to be r1 squared, r2 squared, that's times gain of the transmitter, gain of the receiver, times lambda squared, and times sigma. And that's what it would be for a bistatic antenna setup. Now, the next question that happens on both of these schemes, that's bistatic, this is monostatic, is what's the total delay time? How long does it take, they call it T delay, or simply TD. How long does it take for a pulse to be launched here and come back to the radar? Think about it. This is electromagnetic propagation in considered free space or air. Well, what do you know? The total distance traveled was 2r, isn't it? Because with the radar, it launches, it has to go down, hit it, and come back. So that's total distance traveled, right? And if we divide that by the speed of light, we get the time, right? That's the time delay. So if you just take 2r and divide it by c, that's the time delay. Now, in a simple way to think about this is that would be the time delay that you would use to get the range. I send a pulse, I listen for it, it comes back, I take a look at the time difference between when I send it and when it returns, and I divide that by the speed of light, that's the time delay, right? Which is equal to this, right? And that means the range is what? The actual range is going to be TD times C, the speed of light, divided by 2. Y'all follow me? And that would be the range. It's really, it honestly is this simple. It gets much more complicated because what's actually sent isn't one pulse, it's a series of pulses, and they have a very unique temporal signature. So when you're getting echoes back, you use what's called a correlation function. In some cases, you can use convolution. And whenever when you see the correlation function become a peak, you know that is the point that you can use as the time delay from when it actually occurs, and you know when you send the pulse. That's the way they do this. So that's what the range would be for this setup. How about over here? Well, what's the total range, or the total path length that's transmitted, that the signal goes through from the time it's sent to the time it's received? R1 and R2, right? So R1 plus R2 here would be the total path, right? If we divide that by C now we get the time delay if it's actually a bistatic radar. Now here's the interesting thing with bistatic. You see how the time delay doesn't necessarily give you R1 or R2. Do you all follow me on that? You don't know which one it is, but the time delay is something that's actually available. The way they actually solve these things is, now this type of a target, is they have the aspect angles of these two things, where their peak gains are, and they can actually figure out, just by some basic trigonometry, where that target is. Okay. Now that's basically it for time delay, power density, and the return signal for both monostatic and bistatic. Now, I'm going to talk about Doppler next, and it's going to be just for the monostatic case. So I'm going to erase this. Now we do Doppler. Last time I talked a little bit about the Doppler shift. I said, when you think about something that is Doppler shifted, obviously you've experienced, it's really when you have a car coming at you, you hear the sound, or go to a motor speedway, and then as it passes, it goes, it's now all of a sudden, the perception is that the RPMs have gone down. When they're coming towards you, they seem to go up. Really, they don't change. The thing is that the sound waves get compressed as they're coming at you, and they get elongated when it's going away from you. So for Doppler radar, this is the way, actually, without going into relativity, relativistic Doppler is different. But here, we assume we have a target some range R. Now, this target has a component of velocity in the radial direction. And that's the only component that matters. Right? It doesn't matter how fast it's going in this direction, perpendicular to the radius vector R, but it's the component of velocity in the radial direction. Do y'all follow me? I just call it VR. And this is the radar. So now, this is the simplest way to explain it. Think of the total path length that it moves through. Well, it would be 2R, right? That's the total path of the actual, from the time you set the pulse to the time you return, that would be how far it went, correct? If we divide that by wavelengths, now we have the number of wavelengths that are in that total path from the time it goes out, hits the target, and comes back. You all agree with this? Now, if we take the total number of wavelengths and divide it by, or even multiply it by 2 pi, now what we have is the total phase. That's the total phase change from the time it's sent to the time it hits the target. Do you all follow me on that, class? Find the number of wavelengths multiplied by 2 pi. Now we have phase in radians, right? Now, when we take the derivative of the phase with respect to t, we get something called the Doppler radian frequency. Think about it. The rate of change of phase with time would be the radian frequency. You all follow me? Because that's in radian. That's also equal to 2 pi times the actual Doppler frequency in hertz. And that's also equal to 4 pi over the wavelength times the r dt. That's the change in the radial position with respect to time. Or really, it's 4 pi over lambda times the radial velocity. You all follow me? I'm going to simplify this, but I want you to see the logic in it. Now, after that, I can say, well, if I'm only after Doppler frequency, I can take 2 pi and divide it over here. Now I can find the Doppler frequency shift would be equal to simply 2 times the VR over lambda. And lambda is equal to simply C over F naught, and that's the transmitter frequency. I want to tell you this, that's the shift in frequency that occurs. So if I sent a signal at 1 gigahertz, say it's a radar signal that has a carrier frequency of 1 gigahertz, I send it, it hits target. When it returns, if the target's moving towards it, it will have slightly greater frequency. It would be the transmitting frequency of F, really of 1 gigahertz plus the Doppler shift. If it's moving away, it would be the transmitting frequency minus the Doppler shift. You follow me on that, guys? Now, let me give you a little more perspective on real radar. This is not the Wentworth's book, but you should at least have a total appreciation for what goes on with real radar. There's 2 components to the transmitting a radar signal. The first is called the baseband. Write this down. Baseband signal. What that is basically this. It's usually a signal. It's repetitive for most radars. And this is, for the baseband signal, you can just call this V of T. It can be the voltage of the baseband signal. It has some amplitude A, and it has an on time, this is the 0 point, that's the origin, of tau, and it has a duration of T, and that's usually called the pulse repetition interval, or PRI, but you're familiar with T as period, aren't you, class? When you've had a lot of your coursework. T just means the time over which it repeats itself. This is the baseband waveform. This waveform is multiplied by a very high frequency carrier. So the carrier waveform looks like this. It's very high frequency. And it would just be a constant oscillator like this, if you think about it. This is going to be the carrier, V carrier. Now I'm showing you, it should be like millions and millions of cycles that would occur over a very short time, like 2 periods. You with me? So the actual transmitted signal looks like this. You would multiply this times this. So V transmit of T would be equal to V baseband. I guess I can call it VB baseband of T times V, and this would be the carrier of T. And here's what it really looks like. You're going to have this envelope times that. So it would look like you're going to have something where you have it stops, then it stops. And each one of these has a width tau, and it has a duration T. Now you've had, I think, your radio class, right? Your radio labs where you had, you know that when you talk about a carrier frequency, and then if it's AM, it's just amplitude modulated, and if it's FM, the actual frequency shifts back and forth, right? So those are the 2 types of modulation we've been exposed to. This would be considered amplitude modulation because the amplitude goes from peak to nothing, peak to nothing. And I hope you can see this, right? So now we'll talk about some of the basic stuff of the radar and why we do it that way. And I'll get back to Doppler in a second. This is the most common type of radar. So when we take a look at this signal, right? That's the baseband signal. I want you to take a look at this. If I have an antenna like so, and I have a target out here, with a certain sigma, and it's at a range R as such. When you think about this, the signal goes out, hits it, comes back, I know that 2r is the path length that it went, right? And if I divide this by c, now I get the time delay. TD. That's the time delay it takes a pulse to go out, hit the target, and then return, right? Now, think with me over here. So here's my setup. I send a pulse at this point in time, right? The echo from that pulse has to come back before I send another pulse, or I don't know if this pulse or this pulse is responsible for the echo. Do you all follow me? Can you imagine that? I mean, I can't suppose, just think about a simple echo. Suppose I yell, then I stop. Then I yell again, and then I hear my echo. Right? I don't know if it was the first one or the second one. I can't logically make that claim that is responsible for the returned echo. Do you all follow me on that? So there's a thing called, it's called the maximum unambiguous range. Can I write this down here? Unambiguous range. It's really R sub U is the symbol used in the radar world all the time. It means this is how far we can see and not worry about the target being ambiguous. If it's between, from that range inward, we're fine. If it's beyond that, and we get an echo return, it's ambiguous, but I'll tell you more about this. So this is actually equal. Maximum unambiguous range is going to be, and the way you do it is this. If this is the time period that I have before the next pulse is sent, if I think about, if I send it here, it hits the target there, and then it returns, that means that the maximum unambiguous range would have to be equal to C times the period T divided by 2, or C times the PRI divided by 2, because anything further away than that, I wouldn't be able to tell. This is the maximum unambiguous range. Can you all follow me? C times T would be the distance traveled, right? If I divide that distance by 2, then I know I've got the maximum ambiguous range. What I'm really saying is here, if I transmit at this point, right, then my target, if you think about the time delay, if the target, if it hits right here and then returns here, that's as good as it gets. If I hit the target here, the return would be out here, and I wouldn't know if it was this pulse or this pulse that actually caused the reflection. Can you all follow me, at least on the logic? Now, the truth is this. When you have the maximum ambiguous range for a radar, remember the power falls off as 1 over R to the 4th. What they do is, they're gonna say this is the largest target that we expect to find on our radar. What we do is we set the threshold for more or less what's called a signal and noise ratio, but for the largest target out there at the maximum unambiguous range, the received signal at that range would be at the threshold of detection. So if the target's further than that, I won't see it. Y'all follow me? Now that's basically the way it works with this stuff. There's a lot more to it actually, but this is the concept, the basic concept. So this maximum ambiguous range, that tells me where I should be on the cusp of being able to detect the signal when it returns. Try to understand that you don't want something where if my maximum, if I was able to detect reflections from targets, when the time delay is from here to here, I don't know where that target is. I got 3 pulses that could have caused that echo. Follow me? So that's the reason, that's some of the things that go into engineering a radar. Now, I'll tell you one other thing too. If you have targets coming, by the way, that's important. If you have targets flying at a radar and you have 2 targets radially separated by some distance, I'll call it delta R. If the range difference on these targets falls below a certain minimum, I can't tell if there's one target or 100 targets. Most of you know this, when planes fly in formation in a time of war, they fly in what are called they have basically like a flock of geese. They have an arrowhead shape when they fly, right? They can't have turbulence from one plane affect another, but they fly like this, and they fly very close. And the reason they do is a radar operator can't tell if there's one plane out there or 20 or 100. He doesn't know. He just knows he's getting a return. That's one of the reasons they fly in close formation like that. Very hard to detect numbers. So what is the actual delta R for the time you can detect the target? And if you think about this, with a radar signal, I'm going to give you the formula in a second, but I want to explain. I send out a pulse. The pulse has a certain duration. If you think about just freezing time and looking at the amount of space that the actual wave would be in, it starts here, t equals 0. There's a certain freeze time. That would be the physical dimension that would be affected by it. Let time roll forward. It would be from here to here. Then it hits. The leading edge hits and it starts scattering back. Still, this waveform is going forward. It hits here. Then when it hits this thing, it starts scattering back. Technically, we should have two pulses like this coming back at us. Do y'all follow me? Just think about that. But if all of a sudden these things get too close, we only get one pulse. It's overlap. And that delta R, now this is called the range resolution. Delta R itself is equal to C times tau over 2. Almost identical to range, maximum unambiguous range, but delta R is the range resolution. And it's simply C tau over 2. You can play a little game, and you can literally do something where you can take snapshots in time, increase the time, and see where the actual amount of space is where the waveform occupies, and with two targets. As soon as it gets larger than that, you get two distinct returns back. But when it's anything smaller than that, you only get one return, and you can't tell if there's one or more targets. Y'all follow me? So that's sort of it when it comes to range resolution and maximum unambiguous range. The final thing with radar you have to know, we did Doppler, it's called the signal to noise ratio, what is the critical thing when we do radar, and I'll put it here. And I'm going to give you problems and go through them with you, so you'd be aware of anything that I could ask or require you to know. And I don't go too deep in radar here. I just want to make sure you understand the entirety of it. There's a carrier frequency, it's a pulse waveform like this. And this is called, y'all have heard of signal noise ratio before, haven't you? Didn't you do that in your communications course? Did you have comm yet or not?
Taking it now.
Has he gotten into that?
Yeah.
All right, so when you talk about signal to noise ratio, the symbol is SNR. And what it is really is this. It's the P received back for a single pulse over, this is the power received back, over the noise power. Call it noise power. That's all it is. There's a certain amount of power received back, and there's a certain amount of power in what's called noise. And noise is inevitable whenever you have electronics, because electronics, just because they're not at absolute zero, they have all sorts of shot noise, they have thermal noise, they have all this stuff. And noise is very easy to understand statistically. It has a Gaussian distribution, noise is uncorrelated. So what you actually see is for P received, you know, for P received for radar is what? It's P transmitted, right, times gain of transmitter, gain of receiver, times sigma times lambda squared, over 4 pi cubed, we'll use monostatic, r to the fourth. That's the amount of power received back. Now, I don't expect you to remember this the way I do. I've worked with this all the time. But y'all follow me? That's just the formula we put up earlier, right? the way I always think about it, transmitted power, and it's proportional. Transmitted power, gain transmitter, gain receiver, sigma, which is the radar cross-section, lambda squared on top. On the bottom, it's 4 pi cubed, r to the 4th. We're doing monostat here. Now, noise power, P noise, is usually just p sub n. That's k t times f times b. All right, k is called Boltzmann's constant. And k is 1.38 times 10 to the minus 23rd. And let's see, okay, let's use. Watts per and degree Kelvin. I'll put this up there, I'll put the units and everything. So that's Boltzmann constant. T here is going to be the temperature in Kelvin. So it's the Kelvin temperature, which is about, I think room temperature here is about 290, 270 to 290. I forgot exactly, but typically it's about 290 degrees. Isn't that room temperature, Kelvin? 290? I mean, when they say room temperature, I think they mean 72 degrees, roughly. Okay, so that's the temperature in Kelvin. The F is a noise figure. Let me just tell you a little bit about this. So I call it a fudge factor. Whenever you have any kind of a radar and you have electronics, what you can do is there's measurements you do. We find out based on, without any signal being transmitted, we can measure the amount of apparent noise that is developed. And when we get this noise, we know that this should be the noise power. Do y'all follow me on this? So now, this noise figure we will adjust so that this noise power will equal this equation. This is how they do it. I'm not kidding about this. So this is the equation they're trying to balance. Finally, B is the bandwidth. Now, bandwidth is something you've got you're familiar with that. Bandwidth is what? It's really the frequency range over which the signal is transmitted or operates, right? When you have a pulse signal like this, bandwidth is actually equal to 1 over the on-time tau. And some of you, I'm not going to go too deep into this, but you've had your signals and systems course, right? Okay. You remember when you had a pulse waveform like this? If the pulse was on a length tau and it had a height a, and this is the time limit, if this is the pulse, the symbol at least, you could use a rect function, but we use p tau of t when I taught that. Now that was a symbol for a pulse of width tau centered at the origin at t equals 0. Do y'all remember this? Another one was what? Rect t is the same thing. Rect of, and it would be just t, and I think they put it over tau like that, right? Rect t over tau. You remember rect functions? It doesn't matter what you call them. It's just a pulse of width. It's a square pulse, and it's got a width tau. So this would be tau over 2. This would be minus tau over 2. Now, the actual transform of that, the Fourier transform of that is tau times the sinc function of omega tau over 2. Do y'all remember that? Remember sinc functions? Kind of, sort of? All right, well, here, if you look at this, that's tau times the sinc function. Omega is 2 pi f over 2 is just simply pi f tau. Y'all follow me? So this would be the transform. P tau of t would go to this. Now, in the frequency domain, if you look at this, just so you understand how come bandwidth is 1 over tau. Look at this. I'm gonna plot this. So if I plot the magnitude of this, of tau times the sink of pi f tau, it would look like this. It would have a peak here of tau, this is in the frequency domain, and then it would do this. That would be the envelope of a sinc function, magnitude-wise. Do y'all remember that class? Here's where the bandwidth comes from. You see this first zero right here? How would we find that? Do you remember what a sinc function really is? We have the sinc of x, it's equal to sine of x over x, right? That's the mathematical definition of a sinc function. Sine x over x, where x is the argument of the sinc function. Well, the first zero of this function, I know it's sinc, the sine of 0 is 0, but because it's divided by x, you have to use L'Hopital's rule, it's an actual maximum at x equals 0. The first zero occurs when the sine is 0. So when is sine 0? The sine of x is 0 when x is 0 or pi, isn't it? The next zero is pi, correct? So if you set this argument equal to pi, I'm trying to find this point. So I set this argument, pi f tau equals not 0, but 2, or is equal to pi, then it can be plus or minus pi. Then you divide both sides by pi, and you can see f is equal to 1 over tau, plus or minus 1 over tau. That would be the first zero in the frequency range. Y'all follow me? This would be in the frequency domain for a single pulse. And if you look at this, the bandwidth, since this is centered at 0, this would be the bandwidth to the first null. Do you follow me? Because this would be the bandwidth from here to there. This is assumed centered at 0, which means that this bandwidth is simply 1 over tau. That's how they explain that. And that does work mathematically. It's a very accurate estimate of the bandwidth. Now this is, then when I'm going to get signal and noise, I'll put it over here. I'm going to take this and divide it by noise power, P noise. Now I get this, and I'll put the final thing. The SNR, signal noise ratio for a waveform, will be equal to transmitted power, gain of transmitter, gain of receiver, sigma, lambda squared over 4 pi cubed r to the 4th. That's just the received power from the radar pulse. And then I multiply or divide it by the noise power. And the noise power is K T F B. And that's the standard form for signal to noise ratio for a radar. And by the way, this is a figure of merit. It tells the goodness of the radar. The higher the signal to noise ratio for the worst case target scenario, the better the radar is. Gotta say one more thing too. I'm just gonna throw this out there. That was the signal to noise ratio for one pulse. Now, without getting into the mathematics, we do something where we really have coherency, and I'll explain this in a second, but when we add the effect of multiple pulses, the noise power is not additive, but the actual receive power is, and I'll explain this in a second. So then if you multiply this by the number of pulses n would be the number of pulses sent, then you get the signal to noise ratio for the number of pulses. And here's why I try to make sure you understand this. You all know that noise power is not additive, white noise. It's because it's uncorrelated. So I send a signal, and the signal comes back, and I record that as it comes back in time. So I have a temporal recording of it. It may look like this. My transmit signal will be this. This is going to be baseband. What I receive back has a time delay. Then it comes back greatly reduced and it has noise on it, right? That's one pulse. Now I send another pulse. Get the same basic thing. I'm going to have the same time delay, and what I get back would be this. This would be pulse 2. So it's got noise and the signal. Follow me? And then I send a third pulse. But when I add all these things up, these pulses that I receive, then mathematically I would go ahead and I would do this, of course, use digital signal processing and add them. The noise doesn't add just the signal, follow me? And that's why the number of pulses are so important. Now, I try to hit every aspect of radar that would be of importance. If some of you get into an area where radar is going to be used in it, a lot of you will be. It's been my experience that a lot of the people that I teach EMAG to end up working for either comlinks or radar for the military somewhere in Huntsville, in California, or whatever. And radar is one of those things. I'll just tell you this right now. The types of radar and their uses are just exponentially going up. Here's some of the reasons. You know about how they have really unmanned aerial vehicles and driverless cars, right? Autonomous vehicles. Right? They have to have sensors. They can easily figure out what's in the area, especially for airborne stuff. And the worst thing is, it's real easy to work around planes and stuff like that if everybody is what they call compliant. They have a transponder, everything's working right. But when you get one non-compliant aircraft in space, if you don't have an active radar, you can have collisions left and right. It just happens that way, especially around airports. When you're taking stuff they're doing this in big cities now where they have these, they have drones that are literally delivering packages to landing pads people have. Have you heard of this, guys? All right, in San Francisco and other places. Now this is gonna happen everywhere soon. Well, the problem is when you're flying a drone to a landing pad, it's got to make sure it avoids anything that could really cause trouble, like wires and like tree limbs and things of that nature, things that are unexpected to just happen. And what they need is a sensor to do that. Some of them do have sonars, it's my understanding at least, but the radar is the way to go. And they have to have these radars that are adaptive. They can adapt to the environment to be either a search or track radar kind of thing. And so radar now is evolving to be almost something that's called adaptive radar. And I can't get into all this, but it's a very, very important aspect for a lot of the stuff that's happening with the delivery systems for the post office. Amazon's doing this, Google, I understand, is doing this, Apple. So just be aware that that's the reason I spent more time on this, because you have to at least have the basic aspects down if you go and talk to an interviewer about radars. If they sense you're somewhat familiar, they'll like it. And I'll give you problems that are related to that. Anyway, that's the key signal to noise ratio. Now, what I like doing is a typical problem for Doppler and some of these other ones. I don't like doing a whole lot of theory with at least a few example problems. And as a class, we'll do it, see how you guys handle it. Okay, so here's like a typical kind of problem I would ask. I've got a radar here, and I've got something moving at a velocity, say v equals 100 meters per second at an angle here of, call it 30 degrees. This is going to be the perpendicular R, and this is a target with a radar cross-section of 10 meters squared. Let's say the range is equal to 1 kilometer. I'm putting in everything. So this is the velocity, this is the actual velocity, 100 meters per second. It's got an aspect of 30 degrees down angle there. I'm going to say that the radar has a gain, transmitter gain of 40 dB, which is a lot. I'm going to say the transmitted power is equal to 1 kilowatt. And here's some of the things I'm going to ask. Some of you already can guess. And by the way, I'm gonna say gain of transmitter is gain of receiver, so they use the same gain for transmit and receive, same antenna. The way they do that is they have something that just switches from, it's called a transceiver. It goes from transmit, so now it's actively transmitted, then it breaks the transmission, goes to receive and starts listening. It's just a toggle switch, electronic toggle that allows that to happen. So I got 1 kW, got the range, 1 kilometer, I got a 30 degrees down angle, and now I want to find out something. So, and let me just do this. I'm going to say I have a noise figure of just 1. That way it'll get rid of that part of the equation. And now let me show you my pulse signature. This is the baseband pulse signature. For the radar. It looks like this. And I'm gonna say tau here is going to be 1 microsecond, and this is going to be, wait a second. Let's do something. Instead of making it 1 kilometer, let's make it 10 kilometers. And make this equal to 20 microseconds. And that's repetitive. So that's the baseband pulse. And let the carrier frequency, the transmitting frequency, be 1 gigahertz. Y'all follow me what I'm trying to do here? I got a transmitter frequency is 1 gigahertz, so these things would have a 1 gigahertz oscillation rate inside of 1 microsecond, which means if it's 1 microsecond and that's 1 gigahertz, there would be 1,000 cycles in one of these things. Then it would be dead, then 1,000 cycles. So here's some of the things that have been asked for. First, for a single pulse, I want to know what the power is received back at the radar. So that's the first thing. So how do we do that? Remember, I gave you that, I went through this, you've already had a problem like this, right? So how much power is received back at the radar? Well, you always start with the transmit power, right? Start with 1 kW or 1,000 or 10 to the third. What do I do from there? Divide by
4 pi r squared.
4 pi r squared. So divide by 4 pi r squared, and r is 10 kilometers. So 10 to the 4 squared would be 10 to the 8th, right? Y'all agree with that? Now that's the power density on target, not quite the power density. What do I do next? Sorry.
Multiply by gain.
Right. What does 40 dB translate to gain? Now, I'm going to do this in class, so I won't assume this. Whenever you talk about gain in dB, right, that's equal to 10 times the actual times the log of the linear gain, G. That would be the linear gain. You all follow me? So if you've got 40 dB here, that would be 10 times the log of the linear gain, G. We need the linear gain for the equation I'm using, which means I divide this by 10 and I get 4 is equal to the log of G, and this is log base